Hello, I'm Doug Montgomery, your principal instructor in your Design of Experiments MOOC, and I'd like to welcome you back to our monthly Fireside Chat. For those of you that are new to the MOOC and to the Fireside Chat, this is an event that I host every month with a guest speaker, and we try to explore certain topics, applications of experimental design that we think will be interesting to the participants of our MOOC. Sometimes we talk about things that are extensions of topics from the MOOC, and sometimes we talk about just some really new and I think interesting ideas. We always have time at the end of the guest presentation for a question and answer period. This is a great time for you to ask any questions that you would like. It could either be about the material in the Coursera courses, it could be something related to the guest's topic, or it could be a specific question about a situation that you're dealing with. And we'll try to be able to answer those as best we can. For everybody that's on Coursera, these Fireside Chats recordings are available. They are posted in the resources tab of your course. Couple of comments about etiquette. Please keep your mics muted and your cameras off during the session so that we don't have any extraneous noise or disturbances or things like that. If you want to submit a question to either me or our guest, do that using the chat function on the Zoom menu. And you don't need to wait until the Q&A session actually begins to do that. You can submit that question at any point during the session. Just type it in, and we'll do our best to get two questions during the session. But if we don't get everything answered, we'll respond to it in Coursera for those people that are actually enrolled in the course. Our guest today is Dr. Caleb King. Caleb is a research statistician and developer for the experimental design, the DOE and reliability group at JMP Statistical Discovery Software. Prior to JMP, he worked for 3 years as a senior statistician at Sandia National Labs. Caleb received his master's and Ph.D. in statistics from Virginia Tech. Like me, he's a Hokie. I forgot to wear my Hokie socks today to try to honor our joint connection. But his primary interest is on design and analysis for reliability data. His research interests include design of experiments, reliability analysis, small sample theory, and other sort of interesting topics that he stumbles into, just sort of like me. Okay, so with that, I would like to turn things over to Caleb, and I'm really looking forward to this. This is his second guest appearance, and I'm really interested in this particular topic. So Caleb, it's all yours.
Well, thank you, Doug. And yeah, thanks for allowing me to come back and to speak on a topic that I too find very interesting. This was sort of my area of research for my doctoral work. So I'll share my screen here real quick. There we are. Okay, accelerated testing, or as I like to think of it, boldly going where no traditional DOE dares to tread. So, so I'm going to keep things a little high level here. Just talk about general accelerated testing idea at the beginning, and then I'll be kind of using some software to illustrate how you might walk through planning an accelerated test. I won't talk too much about the analysis side. It's actually kind of straightforward for the analysis. It's the testing side that is interesting to me. So with that, I'd like to start with the motivation. And so what's this whole thing about accelerated testing? What's the point? Well, it's all a matter of time. So let's start with an example that I think everyone can relate to, and that is your cellular device. I'm sure most of us have cellular phones. Probably a good majority of us have iPhones. Another good majority have Androids. And I have no idea what other company fills in the gap there. But we have cellular phones, and I mean, nowadays they're pretty much handheld computers. We check our emails, we play games, we do everything on our phones. So they're very important to us. And so a key component of all of that, of course, is battery life. we'd like our batteries on our phones to last as long as possible. Nobody wants to be in the situation where you have less than 10% left and there's no place to charge it and you are doing something important. Yep, nobody wants to be in that situation. And it's a key part of the advertising for these phones. These phones can last 10 to 12 hours on a single charge, are things that we like to hear. Now, of course, we'd like to know, how did they get that? How do they get that information? How do you determine average battery life? Obviously, there's variety in the life depending on how you use it. So how do you determine that? Or maybe the top 90%, which I actually think is more informative than the average, because if I say the 10 percentile of the lifetime distribution of battery is, say, 8 hours, well, then that tells me good 90% of it is going to be more than 8 hours. So that makes me feel comfortable, at least hoping that I'm in the top 90%. So it's a really important question to know. So how do we get at that? Well, your initial thought might be, okay, I guess maybe when they make the phones, they sit them somewhere, they turn on the phone and they let it sit till the battery dies. That's one way you could do that. It doesn't seem very useful though, because obviously we're using the phones. Not all of us are going to just sit it on a table. It might be on a table somewhere and you use it periodically. Most of the time you might be using it throughout the day. So maybe you could also just maybe hire a bunch of students or something to use the phones and then monitor and see when the battery starts to die out. You could do that, but of course that's going to take time. In this case, it could be several hours. Now, in this case, it's hours, so that might be more reasonable. Let me throw another example at you. How about a light bulb? Those things are hopefully not supposed to last just hours. They're supposed to last months, if not years. And so that's a good thing, but in terms of standard testing of it, nobody has time to wait around months and years for these things to fail. So the question then arises, is there some way that we could accelerate this testing process, because nobody has time to sit for hours, months, or years for their products to fail? We got to get the product out. We've got to get it selling. We got to advertise it. We have other more important things like playing games on our apps on the phones to do. So is there some way that we could maybe accelerate this process to be a little more efficient with our time? And so that led to the idea of accelerated testing. Essentially, maybe we could expose, in this case, our phones, or maybe the light bulb example, to more extreme conditions, which could be either extreme environmental conditions like heat or something, or maybe extreme usage conditions to try and reduce that time frame. So maybe I could take my phone and put it out in the sun. I know sometimes when I go on long trips, I might have my phone up listening to a podcast out in the sun. And so it kind of gets a little hot. So that might be affecting the battery life. Or it could just be I'm listening to an interesting podcast. That could be doing it too. But heat is actually a common environmental accelerator. So we could expose it to some heat. There's also humidity, voltages if it's an electronic device. So these are other types of sort of environmental conditions. It could be a use condition. So maybe, okay, I want to accelerate the lifetime. Maybe I'll open a bunch of tabs on my internet browser. Or this is a personal favorite. Maybe I could watch all 3 of the extended Lord of the Rings films, which are 3 to 4 hours each, back to back on my phone, and judge when in the series it lasts. Maybe it lasts until about the Battle of Helm's Deep. That might be nice. So, little nerd reference there for you. But so obviously these are outlandish kind of examples, but they all kind of get at the idea of we can expose it to more extreme environments to hopefully accelerate it. Now, by doing that, if we're careful about how we select these acceleration factors, as we call them, now you could have other factors that are not necessarily used to accelerate the timescale, but could affect the reliability. So if we're explicitly using them to accelerate the timescale, we call them acceleration factors. If we're careful about those settings, then what we can do is create an experiment, run that experiment to determine how the levels of those factors affect the battery lifetime, and then use that model to then extrapolate back to normal use conditions, as we call it, and estimate the lifetime. And yes, I did say extrapolate. I know if you've taken a standard design of experiments course, extrapolation is a bit of a taboo topic. No, don't extrapolate. That's where the uncertainty lies. That's where dangerous things, there be monsters out there. So here in accelerated testing, we don't care. We're kind of rebels. We say, no, to heck with the rules, to heck with the monsters. We're going to extrapolate. But of course, we have to be smart about it because we do understand that by doing this, there's going to be a lot of uncertainty because we didn't test in that area. So if we're doing it just right, we could perhaps emerge a bit unscathed from this risky endeavor, kind of like this guy with glasses. Look cool doing it. So that's the basic idea behind accelerated testing. We're going to test at more extreme conditions and then use the model to extrapolate back to the use conditions so we get more information in less time, trying to be a little more efficient. Now, how do we actually put this into practice? How does this work? Well, I figured I'd do that by switching over to JMP and just showing you because it's easier to show than tell. And I might have a couple other reasons for doing this. For one, I do happen to work at JMP, so I might be a little biased in terms of the software I'm using. And I mean, I do like the software, and full disclosure, I kind of would like you to like it as well, which is why I'm going to demonstrate for you in JMP. So at this point, I will escape out and come here. I'm going to show you it using the latest version of JMP 17.2. And it's right here under our DOE menu. This is under the special purpose. It's a special purpose type of design, accelerated life test design. And I'll minimize the window so we have only this to deal with. Okay, now I'll kind of walk you through the process of how we go about doing accelerated test because there are some nuances, there are some differences between this and a standard design of experiment. So the first thing is, of course, we're picking our factors. Here in JMP, you can do 1 or 2. I'm going to stick with 1 just so you get the basics of the process. If we want to go back and revisit 2 or more, we can definitely do that. But for the sake of the idea, let's just stick with 1. And I'm going to use our favorite acceleration factor, temperature. Now, some things here that already we start to see, there's this thing called a factor transformation. Most of the time when we're doing these models, these acceleration models, they tend to be nonlinear. One way around that is to do a transformation on the input to kind of linearize it. And a lot of these transformations are based on known chemical and physical processes. So you see this thing called Arrhenius Celsius. This is commonly used with temperature. It's based on what's called an Arrhenius model, which is essentially, for time, it's actually an exponential function of something that's a function of inverse temperature. We usually work on log time scale because it's a little more stable. We like things are a little nicer and easier on log time scale. So in that case, you can just think of it as it's a fancy inverse temperature function. What it technically is there's this big constant divided by temperature on Kelvin. We're working in Celsius, so you do a transformation to Kelvin, which is in this case is easy. You just add 273.15 to your temperature to convert to Kelvin. So it's essentially an inverse relationship with temperature. And there's a couple others. There's the actual reciprocal, which I believe is used more with voltage. There's log, which is often used with humidity, specifically relative humidity. I don't know if I run into anything specific with square root, but that's a common one. And then, of course, you could have, it's a standard linear model. I'm not going to make any transformation. But we usually do a transformation just to make the model nice and linear in that transformed space. We have what are the use conditions for this factor and what are the test conditions. So the use conditions, it could be a single value. So I could have made these both 20. More practically, it's often a range of use conditions. So we're obviously not going to only ever use our phones when it's a certain temperature outside. There will be a range of temperatures that we use it in. So we might want to account for that. Maybe we'll kind of be looking for the average use condition. Now here we specify test conditions. These are the things that we're going to accelerate up to that we hope accelerate the time. Now, of course, in Celsius, this is a bit high for a phone, and that brings up a first good point. One of the things we have to be careful about with accelerated testing is unlike traditional design and experiments where they say, be bold, make those levels as far apart as possible. Don't hold back on it. Accelerated testing, you don't want to be as bold. You want to be a little more cautious because maybe with this temperature setting, if I applied that to my phone, rather than the battery dying out, I might melt my phone. Now, obviously, in use conditions, I'm not using my phone so much that the phone melts. If it is, you might have a problem with your phone. You might need to seek help about that. But in general, we don't expect the phones to melt in our hands after using it too much. So if I apply a certain setting of the temperature in this case that melts my phone, I've introduced a new failure mechanism. I've gone too far. We want to avoid that. I'm going to drop this down just a little bit. Again, it's still probably not a practical example, but for the sake of illustration, we'll do it. So you want to make sure that you pick your ranges so that when it does fail, it is because the battery ran out and not because I melted my phone. Same with the other factors. If it's humidity, you don't want to waterlog your phone. If it's voltage, you don't want to fry your phone. So you always have to be careful how you set those so that you don't introduce a new failure mechanism that wouldn't happen under normal use conditions. All right, so at this point, I'll transition to the next step of the process, which is typically, let me see if I can get this. There we are. It's usually expanded by itself. I did something at the beginning there, but we have to specify some stuff about the underlying model, specifically what is the lifetime distribution and what is the model. So let me start with the distribution. So typically we have in any sort of reliability testing, we have common distribution models that we use for the lifetime. The two most common here are the log normal and the Weibull. Now these belong to a family of what's called log location scale distributions. We do that because, as I mentioned earlier, we sometimes like to work on log time because then everything we can transform things to be nice and linear. Everything's got a real value. It's kind of easier to play with log time. And our distribution models represent that. So log normal, if I say something as a log normal, that just means on the log time scale, it's a normal distribution, which I know how to work with. The Weibull on the log scale has what's called the smallest extreme value distribution, which is why you can see it's called a Weibull because log SCV just doesn't have the same ring to it. So, but the idea is we work on the log, and it's called location scale because there are two parameters. There's a location parameter and a scale parameter. The location, by its very name, determines the location. The scale is sort of how much uncertainty is kind of in there. We're familiar with those type of parameters when we work with distribution models. And so we use that. So the location parameter is what we're going to make a function of the acceleration factors. Now, a quick note, if I back transform to regular time scale, the location parameter becomes what's called a scale parameter on the regular time scale. I apologize that scale is being used in two different contexts here. It's usually a scale and shape parameter distribution. That's what the Weibull distribution is. So in this case, it turns out by doing that location parameter as a function, we actually are affecting the scale of the lifetime distribution, which is what we wanted to do. We want to accelerate the time scale. And so by specifying that model, that tells us, okay, we know now how we at least have some assumption, some idea of how the lifetime distribution is distributed according to some model, and we know how to relate the parameters of that model to the other model, the acceleration model. I'm using model a lot now. So the acceleration model, which I'm going to talk about next. So this was kind of weird because, as to paraphrase a comment I got from a user of our software on a different platform, you're asking me for the answer before I've run the experiment. And I apologize, yes, I am. Because we are extrapolating, the goal of the design is to say there's a certain quantity you want to estimate at the use condition. In fact, you can actually specify what that can be under this ALT criterion. And it's typically a quantile of the lifetime distribution or the probability of failure at some time. Those two are slightly related. Now, of course, we want to reduce our uncertainty about estimating at the use conditions because we're extrapolating. We're going to be extrapolating out. There's a lot more uncertainty. We'd like to make that as small as we possibly can. And so the platform saying, well, in order to do that, I kind of need to have some idea of what that value is going to be. So you need to give me some idea of what you think the acceleration model is. How much are we accelerating? And so this is where you would specify that. Now, you can do that through two ways. One is you can specify the parameters of that model directly. Again, it's a linear type model because we've transformed, so you could specify the intercept and the slope. Or an easier way might be to specify it through quantiles. So here, what we've done is we've kind of done in between. You specify the slope. In this case, because it's Arrhenius, it's actually got a special name. It's called activation energy. And so that's a term from physics and chemistry. So that might be something you know. This beta, this is specific to the Weibull. If I switch to log normal, it's just the scale. So you can see the relationship. The scale parameter on the log time scale is, in this case, 1 over that. So that's a quantity you would know. And then I can specify for the intercept in this case, you just tell me, okay, at this particular temperature setting, I would expect at this time, this proportion of my units to have failed by then. You could also generalize that. You could do that to do both the intercept and the slope. So you could specify it through 2 quantiles. So that might be an easier way to think about it, is saying, okay, at this temperature setting, I expect by this time a certain proportion to fail. So in my case, I'm going to say by about 10 hours, I expect maybe a quarter of my things to fail at 45 degrees C. So that might be a little bit easier to interpret and use to estimate your model than saying, I believe the intercept is -5 and the slope is 1.5, which is a little more abstract. So this is a way that we try and make it a little user-friendly to estimate that. So once you've specified your model, there's some other things you can specify, some uncertainty about the parameters. I'm not going to go into that right now. We can revisit that later if need be. But once you've specified your model and your lifetime distribution, now that we're going to focus on things that are more related to how am I actually going to implement this experiment. So you might hear some candidate runs. Basically, it's taking my temperature. I said, give me 3 levels. Here's my 3 levels. And I can specify things like how many units do I want at each level. In this case, by default, it says it's fair game. I can put any number. I might enforce a minimum and say, okay, at a certain temperature setting, I need at least this number of units. I'll address that later. There's a reason why you might want to do that. So I'm going to skip over this part right now. This is just saying, what am I interested? What do I want to estimate? If it's a quantile, it's the probability of interest. If I had picked failure probability, then you just tell me what's the time range. It could be a single value or a range of interest. I'm going to bring it back to the quantile because that's usually what you're interested in. And next, it's going to ask, okay, how are you actually going to do this design? There's 2 ways. One is I'm going to continuously monitor. So I'm going to put all my samples at their different temperature settings, and I'm just going to have maybe a camera monitor them and keep an eye on them until 1 or more fail, until I've reached the end of my experiment, which I'll say is 20 hours. So I could do it that way. Another way could say, I don't have the time to sit there and watch these things all day. I have other things I have to do. I have other apps I must develop. So maybe I'll periodically go back and check on them. So maybe I'll start every 2 hours. I'll go through and let's do this there we go. So I have equal spacing between my 20 hours. Okay. So basically every 4 hours, I'll come back and I'll see who's failed, what phones have died and what haven't. And in that case, it's a special type of what we call interval censoring. Basically, all I know is that a certain number failed between these time periods. I don't know when they failed exactly. That's the advantage of the continuous monitoring. If you have the time and capability to do that, you would actually know when exactly these failed. That's a lot more informative than just saying, well, it at least failed between 4 p.m. and 8 p.m. When you did this. But I'm going to keep it here under monitoring because that might be something that you practically have to do. And I'll make the design. Now, Jump here is going to give you 2 types of designs. The first one is what we call a balanced design. This is essentially a full factorial design in the factors. That's all it is. It's saying, okay, if I didn't really know a lot about how to specifically design for acceleration factors, let me just do the nice balanced approach. I'm going to equally allocate all my samples against an equal number of equal range between temperatures. Nice balance, everything's great. And one of the things we want to check, though, is the number of failures. So in reliability testing, and especially in accelerated testing, failures are where your information lies. So in this case, you actually want the phone batteries to die. Obviously, in real life, you don't, but here you do, because that provides you information that you can then use to estimate the lifetime distributions. If it passes, that's great, but that's only partial information. I only know it lasted as long as the test lasted. So I don't get as much information as I would from actual failures. So what this is telling us is Well, in this case, it actually expects everything to fail. That's awesome. I'm going to get a lot of information from this. These are all kind of telling you similar thing. This is telling you how many I expect, what's the probability that everybody's censored, so nobody fails, and probability of failure. Okay. Now you'll notice there's this thing called an optimal design. This design says, okay, you gave me a model, an acceleration model. So based on that, I'm going to know kind of what the value is of the quantile is at the use condition. So based on that, I will determine what is the best way to allocate samples and temperature settings to minimize your uncertainty about that thing you want to estimate at the use condition. And what you'll notice is two things. One, it didn't use all the temperature settings. In fact, the optimal designs tend to be very efficient when it comes to the use of number of test settings. Typically, it's on the order of how many parameters I have to estimate, excluding the scale parameter. So in this case, I have a model with a slope and an intercept, so it said, just give me 2. You'll also notice it's very unbalanced. And this is kind of showing that when it comes to acceleration, there's 2 things you're kind of balancing here. One is that whole thing of the extrapolation. Ideally, you might want to put a lot more of your samples at the low end because that's closer to where you're extrapolating to. You don't have to go as far. On the other hand, you also need to balance failures. Remember, that's where your information comes from. And so it's all going to kind of depend. If I go to the lowest test setting, that is closer, so I'm not extrapolating as much, but I might not get as many failures there because I'm not accelerating as high. Versus the higher end, I am accelerating quite a bit. And therefore, I would get a lot more failures. So it's this balancing act that's going on behind the scenes. And so depending on the level of acceleration in your model, in this case, we got a lot of failures. So it's not going to front load as much because it gets a little bit more information here than it does there, I'm assuming. So you're going to see a lot of unbalancing with these types of optimal designs. And then, of course, there's ways that we can evaluate this. So these are the actual variance terms that you would see. There's this D criterion. I don't pay attention to that as much because D-optimality is more something for traditional designs. It doesn't really hold as much for accelerated designs because with accelerated designs, we're doing what's actually called C-optimality. C stands for, I actually don't know what C stands for. So I think a contrast vector. Essentially, you're estimating some quantity and you can do that as a contrast on the information matrix. I'm not going to go into detail on that. Whereas D-optimal is more of just a balance about the model. So because we tend to focus on estimating a quantity rather than the model itself, D-optimal is not really as good for accelerated testing. So what we can look at here is we've got a couple of different profilers. One is this is actually showing you essentially the lifetime distribution. There's time, there's your failure probability. And we can see, especially if I go down to my use condition, there's a lot of uncertainty here. So I know a lot of information up here, but that's where I've accelerated. I'm more interested down here. So there's a lot of uncertainty here. Maybe I could find a way to reduce that. I can go to the next profiler, which talks about something called an R precision factor. So you've heard of margin of error for confidence intervals. An R precision factor is operating the same way, but instead of adding or subtracting it, you multiply and divide by it. So whatever I'm interested in, this case, it's the quantile. I'm going to multiply and divide by the R precision factor. And so, but the same idea applies that I want a small R precision factor. So right now it's very large for what I'm interested in. So what if I doubled my sample size? Let's say I work at Apple, and thus I have all the access to all the iPhones I need to test. In this case, I could significantly reduce my R precision factor. So maybe I could go back and rerun this with 300 and see how does it allocate that way. There's some simulations here. You could, of course, make the table ready to go. And so this is kind of showing you how you would actually lay out the plan. It's a very small table, but it's essentially saying, given how many you're going to be, you're estimating, I believe here, you'll have 64 at the 80, 86 at the 90. All you have to record is how many failed prior to your first check-in, your second check-in, your third, and so forth. If this were continuous, then it actually might expand it out. And so you'd have an entry for each one. So you could put in the actual failure time or whether it was censored. because of this interval censoring, all you need to know is how many out of the total failed. And so there's a script ready for you to go once you're done. Okay. Now, at this point, there's a couple other things I want to talk about specifically with these designs that we've laid out. There's an extra type of design, and I want to kind of show you what that looks like. In order to do that, though, I am going to have to really, really force my hand here and give you a sneak peek at what's coming out in JMP 18. For you see, there's a new platform called Constant Stress Accelerated Live Test Design. And you'll notice it's got a bit of a similar format. Things are hiding, so I can't drag it down. But I've got things set up about similar to what we did before. Here we go. Now I can drag stuff around. And it's going to walk you through the same procedure. So you have your model. What are you interested in testing? How many things are you going to test? I'm going to try and set things up similar to how we did before. Now, there are some differences. You'll notice that I specify everything through quantiles. I even give you a graph. So I'll set things up. I think it was 0.25 at 10. And I'll say at 80, that's going to drop down to 0.1 at 10 hours. There we are. So we've got some, the y-will beta here should actually be 0.5 because it was 2 for 1 over that earlier. So I'll make a test plans now. And here I've displayed for you something called a compromise plan. So why do I have that? The compromise plan comes about because the optimal plan is really good at being very efficient in getting you the values you want if the model you gave it is absolutely 100% correct. If there is any uncertainty about that model, then you're going to be kind of screwed with the optimal plan because it's too reliant on that underlying model. So one area that you could get messed up is it assumes a linear model. What if there's curvature even after I transform? What if there's curvature in that model? Well, the optimal plan gave me 2 levels. I'm going to have no way to test for that. So if there was curvature, I have no way to detect it with the optimal. Compromise, and that's the name of the plan, is maybe I'll throw in an extra level just in case. I'm going to lose out a little bit on my uncertainty, but the trade-off is that I'm a little more robust against model misspecification. I also might have some protection if the parameters are a little bit off, maybe, but that's also something you want to assess, which is why in this new platform, in addition to those previous diagnostics, I also have a model sensitivity profiler. So you can actually see if I specified something incorrectly, how much sensitivity is there. In this case, not too much, not a lot of sensitivity. Curves are relatively flat, good to know. So in this case, if we compare across plans, in this case, the compromise actually did a little worse than the balanced. I will admit fully that I'm still tweaking things in this platform, so. But it can happen that the balanced plan, in fact, if we look at it, the compromise and the balance aren't that far off. Now, where things might start to differ is if I throw in more factors, more acceleration factors, because our balanced plan is a full factorial. It's going to blow up really quick. The compromise, not so much. It's actually just an extension of the optimal plan. But again, it's important to kind of assess what those trade-offs are in this case. So we can look at things like the R precision factor. Again, that's margin of error. I've got standard deviation of the log failure probability. I've got things on the log scale because again, we like things on the log scale, things nice and behaved on the log scale. So that's kind of an overview of the flow of the process. So when you run the experiments, it's going to work kind of almost like a standard reliability, except now we got some extra acceleration factors to develop a model to extrapolate back. So at this point, I'm going to back out of JMP real quick, and let's get back to those slides. All right. So what are some things we kind of learned about accelerated testing in general? Well, hopefully you've picked up on what I call these principles of accelerated testing. There's actually a paper by Dr. Bill Meeker, who was a prominent researcher in this area. He actually had two of them. The first one was pitfalls of accelerated testing, and then there was a pitfalls 2, if you will. So this kind of touches on some of that. I'm going to encourage you to go check out that paper if you want, because there are some nuances, again, with this type of testing. So first of all, as opposed to standard designed experiments where they tell you be bold with your settings, accelerated testing, don't be that bold. You might want to be a little less bold, because if you set it too high, again, you could end up with a melted phone instead of a phone that's just waiting to be recharged. So we have to be careful with our settings that we don't introduce new failure methods that we wouldn't see in the use conditions, because then we can't extrapolate correctly. And here, typically with your standard designs, optimal designs are good because they're tailored to your specific situation. Now, optimal designs and accelerated life testings are tailored to the setting, but they tend to be over-reliant under the underlying model, which you already kind of had to guess at, unless maybe you're using a previous version of the iPhone and you trust its model, in which case, great, you might be okay using an optimal design. But if not, it's going to be a little too reliant. So that's why we introduce things like a compromise plan. We'll throw in an extra level, but we'll be smart about how we pick that. We let the software choose that, but we're going to do that so that we're a little more robust against model misspecification. So there's a slight change in the application. And again, here, unlike in the real world where we don't like to see failures, here we want to see failures. In fact, that's the general rule in reliability testing. Failures give you more information than passing does. Passes only give you partial information. Failures give you a lot more information. And that feeds into how the designs are made. A good design is going to balance having a lot of failures with less extrapolation. You want a lot of those failures to get you more information, which is, again, why you want to pick your test rating, test settings, the levels there pretty well, so that you will get failures. If you're a little too broad, you'll either melt your phone or you're not accelerated enough to get failures. And so you're not going to get the information you need. And again, that leads into this idea of the unbalancing. Balanced designs are nice. They have a nice symmetry about them. They are aesthetically pleasing, and they also do pretty well in terms of estimating things. But typically in accelerated testing, we will probably end up with an unbalanced design. Again, because we need to balance, we need failures, but we also don't want to extrapolate too far. So there tends to be some unbalancing going on. It's possible that an unbalanced compromise design is going to be a lot more informative than a balanced design, potentially. All right, so that's accelerated testing, especially accelerated life testing, where the responses pass-fail in a nutshell. Now, of course, there's a lot of variations that we can do on this, so I'll briefly talk about some of those. So what are ways that we can extend this idea? Well, we touched on it briefly, saying, you can have multiple acceleration factors. Most of the experience has been up to 2, maybe 3 acceleration factors. Typically not more than that, at least from Bill Meeker's experience, who I've talked with. He said he almost never encountered a 3-factor design with 3 acceleration factors. Could happen, but it's very rare. But if you do have that, it turns out the way that you can create those designs is actually not too much different from what you do for a single factor. In fact, you can essentially collapse it down to a single factor space, if you will, create your designs there, and then split it back out to the multi-dimensional multi-factor case. Bill has a paper with himself and Escobar on accelerated testing for 2 or more factors that uses this idea. I actually use it in the platform coming out in Jump 18, and it made things a whole lot easier for me, because I only had to figure out how to do things for 1 factor and then splitting out to multiple factors. Relatively straightforward. There were some hiccups, but relatively straightforward. So we can, of course, combine multiple acceleration factors. And you can even include different types of acceleration. So what I described was constant stress. I hold the temperature in the oven at a certain setting. Now, you could do stuff like a step stress, where up to a certain time, or maybe up to a certain number of failed products, I keep the level constant. But once I reach that time, it's before the actual termination of the test, I step up, I increase that level. And the idea is that I want to get more failures. Now, the complication becomes that instead of a nice constant level, for that setting, I actually have 2, potentially even 3 step stresses that I have to account for. And so how that affects the acceleration needs to be accounted for. And there's variations I can step up. There's even variations where I can step down in the acceleration, which is kind of an interesting trick. There's also ramp stress, which is essentially take the step stress to its logical limit. In this case, I start with a setting and then I determine the rate at which it increases over the test. So it always increases until the end of the test. So that's called a ramp stress. And then there's a special type called fatigue testing, where it's kind of like the step stress, except that instead of stepping up and staying up, you cycle. This is most commonly done with materials where they might experience some sort of a vibration, such as in aircraft or buildings. So the fatigue testing, you're going to be pulling and pushing, or pulling and pulling a little bit less on these little test coupons until they break. And so in that case, what you determine is the maximum and minimum stress is going to experience over that cycling. And then finally, we can even have different observation types. So what we talked about is accelerated life testing, where I'm interested in pass or fail. Now with this iPhone experiment, a lot of you might have been screaming at me in your mind, when you go and test, why do you have to wait to see if it's dead? Why don't you just look at how much percentage is left? And I'd say you're absolutely right. I was purposely being very impractical with my example. Obviously, with the battery example, you could go in and look at, okay, how much is it degraded? And that's the exact idea behind degradation testing is instead of having to wait for a pass fail, I actually get to watch some sort of continuous measure degrade. It could be a decrease, it could be an increase. But I'm watching something change over time. And this is actually a lot more informative than pass fail, because if it survives till the end of the test, I can actually see how close it got. Maybe I define some threshold in the battery example. Maybe I say 10% it's failed. We call that a soft failure. You could also do the hard failure, which is it went to 0. But in either case, you can actually see how close it got. And that gives you a lot more information now. So rather than having the partial information from censoring, you actually have a lot of information about that lifetime distribution. Now, the complication is that in addition to an acceleration model, I have to specify a model for how the path will degrade. Is it linear? Is it nonlinear? And then I have to specify how does that curve relate to my acceleration model. So there's a little bit more complication to that, but the benefits are that you get a lot more information. And of course, there's other ways that you can extend these accelerated ideas. I've seen things where there's partial acceleration. So you actually pick some levels that don't accelerate all the way. They're actually closer to the use conditions. And so that way you don't have to extrapolate as much. I'm trying to think of some others that I've seen, but I think this pretty much covers most of the type of testing that you might encounter. So with that, I'm going to stop there. I hope you enjoyed my 10,000 foot look at accelerated testing, and also a brief look at how you can do it in JMP, both now and in the future. So I'll take any questions you have at this time.
Yeah, thank you very much. This has been a very enjoyable presentation. I learned some things.
Nice.
About accelerated testing that I probably didn't really fully understand. One of the things I thought you mentioned at the end was pretty interesting, which is I guess what I've thought of as fatigue testing, where you shake or vibrate something until it fails.
Mm-hmm.
And I sort of had some peripheral involvement with this with one of my Ph.D. students a number of years ago. He was a Honeywell engineer,
Okay.
and he was involved in their avionics products, and was trying to develop a transition mechanism to lead-free solder for the printed circuit board components used in their aviation products. And they were very interested, of course, in what kind of difference would you see in the reliability of these printed circuit boards if you switched everything over to lead-free solder. And principally what they did was a lot of vibration testing.
Mm-hmm.
They didn't accelerate with temperature or anything like that, because
Right.
the logic was that these devices, when they were installed in the airplane, were maintained at cabin temperature. And so, you know, they weren't going to be exposed to extremes of heat and cold, but they could get a lot of vibration. So they had these test platforms where they could you know, shake the heck out of these units, okay, and see if they could get either wires to break or the bonds themselves to fail.
Mm-hmm.
And he was you know, some of that work showed up in his dissertation, and I always felt like it was an area that I should have pressed him to do more with in some of the modeling and the analysis, but he had already done quite a lot in terms of just the solder chemistry,
Right.
part of the work. And but it was quite interesting, and so this is something that we are going to be able to do in JMP, is to deal with these kinds of experiments as well.
Mm-hmm. And in fact, coming out in JMP 18, so my colleague Pang is working on a fatigue life data analysis platform where you would actually analyze fatigue data. So that's actually pretty exciting.
Yeah. Well, the data that he got was strictly pass fail. You know,
Okay. Yep.
there wasn't any really way to look at the degradation
Mm-hmm.
of the solder joint or the wire, but you could pretty easily tell whether it failed or not.
Right.
And that was the primary response that he had used. I was always fascinated by that. In fact, I've talked to Bill Meeker, whose name you mentioned a couple of times about this, and I've always found him to be a very informative resource. And I am familiar with one of his papers, the first one you mentioned. You know, the sort of what can go wrong with reliability testing. But I'm not too familiar with the second one. Are those both technometrics papers, or
I kind of want to say yes.
I'm just
It
not
might be because the first one is pitfalls of accelerated testing, and then I think the second one's labeled more pitfalls
yeah
of accelerated testing. So
yeah, it makes sense that they're both technometrics papers.
yeah.
Oh, we've got a question.
Yep, we do. So does this also handle the type of accelerated testing where you stress a sample until it fails specifications? I kind of want to say yes. So it all really depends on how you define a failure. So it can be like Doug described, there's the obvious, I look at it and it's the solder joint's now split. So obvious failure. My phone example, the battery went to 0. Obvious failure. You could also have something where, and in fact, I ran into a lot of this when I was at Sandia. They would do specific type of environmental testing, and so they would have set up these specifications for the thing they're testing. And yeah, you would stress it until it fails specifications. So yeah, it really all depends on how you define, what do I define by a failure? And again, the accelerated testing part of it is just that you're putting it under more extreme environments than you would expect it to actually encounter. That's the accelerated nature of it. So hopefully that answers the question. I would say yeah.
It would seem to me that it just depends on how you define a failure.
Exactly.
Yeah, that's the way I would interpret that.
Mm-hmm. Yep.
Speaking of failures, I do have a question that occurred to me. You know, when you accelerate temperature, let's say,
Yep.
And say you have two levels. One of your levels is closer to the condition of use, and then the other one is potentially much further away.
Right.
I would expect to get more failures at the further and most remote temperature condition.
Yes.
But you always want to have some at the lower level.
Exactly.
Is there any sort of guidance about how many failures that you should hope to get in order to get good estimates of life at use condition?
That is an excellent question. I've never been able to kind of really find a good rule of thumb as to what that is.
Okay.
Because I've seen it in the software I'm developing, I've seen it in this one. There doesn't seem to be some number around where, okay, the probability of failure fell below this value, so now it's just going to avoid that versus, oh, it's above this value, now it's going to assign it. Yeah, and that definitely gets at that idea of the balancing act. So in the situation you described, it's going to be really difficult because you want some definitely at the low end. I could almost see that one. Um, I that one might be a lot more front loaded in terms of an optimal design, because if you're high enough that you're going to almost guarantee to get failures, then that's just whatever you assign there's going to fail. So it's how much do you want to put there? At the low end, because it is a lot closer and it's a lot harder to get failures, it might front load it because that increases your chances of getting those failures.
Yeah.
It's small, so the more I assign there, the more likely I'll get something. The other one's just sort of, I'm getting information, so whatever I put there now. So that's just my intuition, though.
Well,
I'm
it's
not
kind of a
entirely sure if there's
sample.
a
It's kind of a sample size problem too.
exactly.
How many units can you afford to test? If
Mhm.
you're looking at units that are either expensive or that are complicated to manufacture for purposes
Right.
of test, then having some idea about what proportion of those you would want to fail at the lower stress condition
Yeah.
is kind of an important number.
Exactly.
Because if you say, okay, I'm going to test 10 there, okay,
Yeah.
and you guess wrong and you get no failures, you're sort of stuck.
Mhm.
You really are. You really haven't learned much at all. Uh,
Right.
so
Exactly.
if you had one or two failures, is that enough to actually learn anything?
Yeah.
That's the scary part of this to me, which in a traditional experimental design setting, I kind of think of, okay, I'm going to do enough replication to have adequate power.
Right.
And to me, adequate power is I'm going to want to have a power of 75 to 80% to detect an effect size of, say, 2 standard deviations.
Yep.
That's the kind of rule of thumb that I teach my students in basic experimental design. But here it seems to be a lot more nebulous in terms of there to me there is an analogy of something like that power mindset that that would be helpful in
Right.
in determining how many samples you need to test in order
Exactly.
to get a reasonable number of failures to learn something that's useful at your standard use conditions.
Right. And yeah, I mean the closest I can think of, I mean, is the standard way we do it, which is you're specifying something you want to measure, and it's the uncertainty around that you want to
Mm-hmm.
try and minimize. But I get the point of it's a little bit harder to think, well, let's say I just pick the two levels, and then how many do I assign to the lower end to do that? That one I'm not as entirely clear on. I think it's because it depends on a lot of factors. There's what is the distribution model, because it can
Mm-hmm.
change depending on that. That's what's driving the failure probability. Um, and then of course, what is that setting? So I guess Now that I think about it, yeah, it is the probability of failure that is going to drive that. And that's going to depend on the acceleration model and the distribution model. How much does it accelerate? And then what does the general uncertainty structure look like? And which is why it's a little more nebulous, because unlike in standard design where we typically have the underlying normal assumption, here it could be log normal y, it could be a couple of other things, and the answer is going to change depending on that. But just
It's
me spitballing is, I think a good rule of thumb would be if you could specify something about that failure probability in general. Um,
is this something that is this an area where some kind of pilot testing might be useful?
yes, absolutely.
Because that's one of the things that I've often recommended in the world of standard experimental designs. If you don't know anything about how much variability is in the system, then pick a test combination that looks interesting in your experiment and go run the darn thing.
Yeah.
3 or 4 times
hmm
and see what happens.
Yeah.
And it might, the conditions you pick might even be your normal operating conditions, so you don't waste material. But
Right.
but go do some repeat runs, some replicate runs, and get an idea how big the noise is. Well, maybe that idea could be utilized here somehow.
Exactly. Yeah. You could use that same thing, but maybe at at a higher acceleration, so you
Yeah,
you will see failures.
yeah.
Um, and yeah, same basic idea. Just take a couple, let's run it there and get some failures so we have some idea of what that distribution kind of looks like, or at least some idea of what that probability of failure is.
Would
But yeah, a pilot testing is very important, because with the accelerated life testing, at least the way it's set up, you guess wrong, you could be really far off.
Yeah,
So
that's what I'm afraid of.
so
Uh,
it's really important that you have some information. This isn't something you just run off the bat.
yeah,
You got
yeah.
to have some idea going in of what you're doing.
And I would think that the situation might be a little easier if your response was a degradation rather
Yeah.
than a 0-1.
Yep. Exactly.
Is my thinking right?
It's absolutely right. Yep.
And would more levels be useful instead of having, say, a low and a high, maybe a low and a middle and a high?
hmm
Would that maybe make the situation less murky? you know,
Probably. So, I mean, that's the reasoning behind the compromise is
yeah,
the optimal is just way too dependent. So if you let go of that dependency a little bit, then if I add a couple more levels, you at least get a better sense of what that underlying acceleration structure looks like,
right.
which is going to help you because you are extrapolating. So if there's any change there, you want to capture that.
And you're really kind of extrapolating in a nonlinear world. So
Yes.
more than 2 levels is probably good practical advice.
hmm Absolutely.
I think that's
Yep.
I mean when I see people using 2-level designs, for example, in classical experimental design, I always try to look around and say, is there a way we can add say center runs to this
hmm
design to get some additional information just in case there's stuff going on out there that like this
Yep.
that we don't anticipate.
Exactly.
Because
Yep.
having done this kind of thing for 50 odd years, I've seen that kind of thing happen enough to be interested in getting insurance.
Yep.
And so the idea of more than 2 levels is helpful here too.
Yes. So yeah, the optimal design is kind of nice as an initial guide point, but yeah, when you actually run it, you don't want to do 2 levels. You want more. So
Yeah.
yeah.
So that's useful. That's useful information.
Mhm.
And I think it would be possible to set up levels where you could test a fairly small number of units in a pilot testing
Mhm.
framework and get some idea about what sort of failure probabilities you're going to get.
Exactly. Yep.
Well, this has been extremely useful.
All right,
I
excellent.
I have learned a lot.
Nice.
It's been useful to exchange some ideas with you about this. We have come to the end of today's session.
All right.
Our next Fireside Chat is in November. It's November 15th. And there'll be more information about that. And you can find the recording of this session in the resources tab in Coursera. Look forward to seeing everybody next month. And Caleb, I can't thank you enough for taking time out of your incredibly busy schedule to do this. And
Sure.
I really do appreciate it. Thank you again very much.
No, you're welcome. Thank you for having me.